We are going to pick up where we left off on Thursday. Most classes actually did see number 8. I had one class that did not, so I want to go through it along with all the ones on the back. We'll go pretty fast through this because we've been doing factoring, and I think most of you guys have gotten pretty good at it. I hope that you feel comfortable with it. So we are going to just roll right through this, and then I don't know if you've gotten the worksheet yet, but there should be another one that's coming, and it has to do with simplifying radicals. So we're going to move straight from this homework assignment over solving quadratics by factoring, and we'll move directly into simplifying radicals. You do need a calculator, so if you haven't grabbed one of those, make sure you get one because they're important today. So let's look at number 8. Number 8, of course, was the last one where step 1 was already done. Everything is on one side, so we can go straight into factoring. So let me kind of catch you guys back up because I know it's been a couple days. But remember, here's what I hope that you guys notice. First of all, there's 1, 2, 3 terms. And if you notice, there's no number that will go into 6, 5, and 4. And 4 doesn't have a variable. So there's no GCF. So the only way we factored trinomials is factoring into 2 binomials. But hopefully you guys notice that your A value is not a 1. So we're going to use the over-under method. Okay? So I'm going to rewrite this. So it's x squared plus 5x. And then 6 times negative 4 is negative 24. And this is what we're going to factor. Easy style factoring that we've been doing. So we're going to make our 2 binomials, and of course, what multiplies by itself to get x squared? We've said over and over, that's x times x. Then, what multiplies to get a negative? Well, that's positive and negative. So again, remember, they're working against each other. So we're looking for the 2 numbers that multiply to get 24, but because those signs are opposite, they have a difference of 5. Now, again, you're welcome to go and to look at those values, but those values are 8 and 3. 8 times 3 gives me 24, and the difference between 8 and 3 is 5. So the last thing I do is I say, hey, plus wins. So when these 2 numbers are going at it, when they're fighting, 8, the bigger factor, has to go with that plus sign because it needs to win. So we've got 8 here, and we've got 3 here. So almost done. We also have to remember to come back under. And if it will reduce, we reduce it. You see, 8 over 6 reduces to 4 over 3. And then 3 over 6 reduces it to 1 over 2. Now, when we had a couple like this in our notes, remember, we're not factoring. We're solving by factoring. So the reason I say that is because I don't need to rewrite these as factors. I just need to take what I have and set it equal to 0 and solve. That'll save me a step. I don't have to worry about rewriting these as 3x plus 4 and 2x minus 1. It won't help me. It'll actually just make an extra step solving. So here I'm going to subtract 4/3. So x equals negative 4/3. And then I'm going to add 1/2. So x equals positive 1/2. So negative 4/3 and positive 1/2 are my zeros. My solutions, I should say. We haven't really called them zeros, but that's the direction we're going. Okay, let's keep on moving, and I'm going to go pretty fast, so please try to keep up. Here, I know that I have this x squared on the right side. I need to move it over here to the 7x squared. So I'm going to subtract it. Well, 7x squared minus 1x squared is 6x squared. And then plus 8x equals 0. Now again, remember, go through your process of thinking here. It's 1, 2 terms, binomial. And is there a greatest common factor that I can pull out of 6 and 8? Well, for sure. They're both divisible by 2. But then also, look, this has x squared, this has x. I can pull out 2x. So remember, that's an important factor. So here I go. I'm going to pull it out of both terms. So 6 divided by 2 is 3. And x squared divided by x, one of those will cancel and leave me with just x, so 3x. Now we move along to this term. Positive 8 divided by 2 is plus 4. And then, of course, x divided by x will cancel. Now, if I take these two factors, so 2x, set it equal to 0, and 3x plus 4 and set it equal to 0, now I can solve and find my solutions. So I'm going to divide by 2 here, so 0 divided by 2 is 0. Here I need to subtract 4 and divide by 3. So negative 4/3. So there they are. X equals 0 and x equals negative 4/3. There's number 10. Let's keep on moving right along to number 12. Again, I'm going to get everything on one side. So that's going to require me adding the x squared to the 3x squared. But then don't forget, this 81 also needs to come over. So we're just going to subtract 81. So here's what it leaves me with. 3x squared plus 1x squared is 4x squared. And then, of course, minus 81. So here's my process of thinking, okay? Remember, I'm going to look at this and say, hey, it's a binomial. Two terms, 1, 2. I can't pull a number out of 4 and 81. 4 won't go into 81. 2 won't go into 81. So I have no GCF. Look, this one doesn't have an x like that previous one. So what is the only other way we talked about factoring binomials? Difference of squares. And sure enough, 4x squared is a perfect square. And 81 is a perfect square, which we're going to be talking about those a little bit more today. So I'm going to factor these. Remember I told you it's the one time a binomial factors into two binomials. So all I got to do is say, hey, what multiplied by itself to get 4x squared? Well, that's 2x times 2x. And then what multiplied by itself to get 81? Well, that's 9 and 9. And then the rule of difference of square is one of these has to be positive and the other has to be minus. So therefore, I'm going to set 2x plus 9 equal to 0 and 2x minus 9 equal to 0. This one I'm going to have to subtract the 9. So it'll be negative. I'll divide by 2. So that's negative 9 over 2, or some people maybe change that to negative 4.5. This one I'm going to add 9 and divide by 2. So it's either positive 9/2 or, like I said, positive 4.5. And there they are. Those are my solutions for number 12. Moving on to number 14. Looks like we got quite a bit to move here. So let's get started. I'm going to subtract this x from the 11x. Why? Like terms. I'm going to subtract this 4 from the 25. Same reason, like terms. So here we go. Let's see what we're left with. Well, x squared is going to drop straight down. 11x minus 1x is positive 10x. And then positive 29 minus 4 is positive 25. So there we have it. Okay, let's see what we got here. We got 1, 2, 3 terms. Okay, trinomial. I cannot pull out a common factor because look, this has no number. It's understood to be a 1. I can't pull 1 out of all this. 25 doesn't have a variable, so there's no GCF. So how have we factored 1, 2, 3 terms, trinomials, into 2 binomials? And once again, since my A value is 1, we don't have to worry about the over-under, because think about it, I'm just going over with the 1, under with the 1. That's not going to help me. So we get to go straight into factoring. So what multiplies by itself to get x squared? X times x. This time, what multiplies to get a positive? Remember the rule, it's either 2 positives or 2 negatives. So I look right here, it's got to be 2 positives. So plus, plus. So I'm looking for the 2 numbers, the only 2 numbers that exist, that will multiply to get 25 and combine to get a 10. So that's 5 and 5. So there it is. There's my solutions. Now think about it. Aren't those the exact same solutions? Is there any reason for me to write those down twice and solve? No. So I really have only one solution, and we're going to talk about this later. How does that work? Well, it's called multiplicity. Let me explain real quick. Here's why this happens. Remember, we're talking about a quadratic. That's what this whole thing has been. And most of our answers have had two solutions because they cross our x-axis in two locations. So why is it possible, or how is it possible, that I would have the same factor twice, which really gives me the same solution twice, -5? Well, here's what it means, y'all. It means that right here at -5, this graph is not crossing through it. It's coming down and it's hitting it, and then it's going right back up. So how many times would this cross the x-axis? Well, none. It only touches it. It actually doesn't cross it and go back up. It just touches it right at -5. So -5 is my answer with what we would call a multiplicity of 2. And we'll talk about that later. 16. Let's knock it out. Let's get all of our like terms. So I'm going to subtract 2 from here. I'm going to add 3x to there. So 4x squared drops down. 41x plus 3x is 44x. And then 98 minus 2 is 96. Now listen, I saw a couple of people working on this problem on Thursday of last week. And here's what you did. You said, hey, that's a trinomial, and my a value is not 1. So you did the over-under, and you multiplied 4 by 96, and then you factored it. Guys, you forgot the easiest thing, and that is there a greatest common factor? You see, there is. I can pull 4 out of every single one of these terms. Now look, I can't pull x out. 96 doesn't have one. So all I can do is pull out a 4. Now look, 4x squared divided by 4 is x squared. 44x divided by 4 is positive 11x. And then 96 divided by 4 is positive 24. So here's the point. When I'm solving and not just factoring, this factor is kind of unimportant because 4 can't equal 0. And since it doesn't have a variable, we just let it cancel. Let me go back so I make sure and clarify this. Up here, when I pulled the 2x out, 2x was important because it's got a variable with it. So I had to take it and set it equal to 0 and solve because it caused one of my solutions to be 0. I hope you understand the difference between that and pulling out a 4. See, 4 doesn't have a variable, so really it's not important as far as the solution goes. Now, it helped me clean this up, so now I can factor this into two binomials. And I'm going to go pretty fast. X times x. To multiply, get a positive. It's plus and plus because of the middle sign. So we're looking for two numbers that multiply to get 24, combined to get 11. Well, that's 8 and 3. And those will give me my two solutions. X will equal -8. Set x plus 3 equal to 0. So x will also give me -3. So I went pretty fast, but I think you guys hopefully understand at this point. Last one, and then we'll move on to today's lesson. Here, I need to get everything on one side. So I'm going to subtract the x from the -11x. But then that 9, I'm just going to move it over. I don't have anything to move it to, so I'm just going to put it at the end because it's a constant. So here's what I'm left with. 4x squared. -11 minus 1 is -12. And then, of course, we had to add that 9 to move it over. So here's what I'm left with. Now, don't think just because we pulled a 4 out of the last one, we've got to pull some. Look at it. It's 1, 2, 3 terms, trinomial, and it has no GCF. Look, 4 won't come out of 9. It'll come out of 12, yeah, but it won't come out of 9. It's got to go into all 3 terms to be a greatest common factor. So it's not. So we can't pull out a GCF. So we have to factor this one. Well, again, it's a trinomial. So we're going to factor using or into two binomials. But since my A value is not 1, it's a 4, we're going to do the over-under method. Here we go. X squared minus 12x, and then 4 times positive 9 is positive 36. So we factor this easy style. X times x, right? To multiply to get a positive, but that middle sign being a minus, these will both be minus. So we're looking for the two numbers that multiply to get 36, combined, because the signs are the same, to get a 12. Well, that's 6 and 6. Now, don't forget, and these are the same, I know, so we're going to come back under with a 4, and sure enough, we're going to have the same factor twice. Very, very similar to what we had up here on 14. So once again, I'm going to reduce these to 3 over 2, because that's what that will reduce to. But since they're identical, I only need to take one of them and set it equal to 0. So I would add 3/4, and that would be my answer. Either that or 0.75. So hopefully after me explaining the one above, you would understand that in this particular case, this quadratic would come right down here to approximately 0.75, and that graph would come down and touch it right there and go right back up. That's how that graph would look, something similar to that. So there you have it, guys. This is solving by factoring. We've spent quite a bit of time last week on factoring, so hopefully you guys start to feel pretty good about this. So put that away if you hold on to it, because you're going to show me that tomorrow, and I'll give you a grade on it. So hold on to that tomorrow. When I come around and check tonight's homework, we're going to check both of them, okay? We're going to look at both. So here we go. Today we're talking about simplifying radicals. And hey, listen, we're going to keep this really simple, okay? It's gonna be pretty easy, but we're gonna try to make it as easy as possible. You see, tomorrow, Wednesday, we're going to start using this thing called the quadratic formula. Quadratic formula is the catch-all on how to solve quadratics. So we already talked about solving by factoring, but I'm also going to show you guys how to solve using the quadratic formula. In order to solve using the quadratic formula, we have to be able to reduce radicals. So let me explain what that looks like. Okay, first of all, a radical symbol looks kind of like this. It looks like a check mark with a house on top. Maybe you've seen that before. Now, this one in particular is called a square root. You see, a square root is understood to be a 2 there. Now, they'll never put it. If they ever intend it to be something other than a square root, they will put the number there. Like that would be a cube root, that would be a 4th root, so on and so forth. When they don't write anything, it's understood to be a square root. This is a radical, okay? A radical. Square root, when there's no number there, it's understood to be a 2. Now, listen, what I like you guys to consider is this thing is like a prison. And the only thing that has the ability to break out of this prison are these numbers that we call perfect squares. You see, a perfect square is a number that you get when you multiply something by itself. So if you were to go to your calculator, and let me do that real quick so you can see this. If you were to go to your calculator, there's a couple buttons here that are important. So give me a second as it loads up. And let me reset the calculator real quick. There's a couple buttons that are important. One is the x squared. And right above it, you see your square root, your radical. If I wanted to check to see if something was a perfect square, I would go second, square root, and then I'd put the number in there. So let's start with something easy like 100. Is the square root of 100 a perfect square? Well, is 100 a perfect square? Yes. Why? Because 10 times 10 gives me 100. So look, if I did 10 and I squared it, look at that. It gives me 100. So 100 gets to break out of the radical as a whole number 10 because it's a perfect square. I hope you understand that. It's a pretty simple concept. So here are the first 20 perfect squares that could potentially break out of a radical. Now, the first one, of course, is what's 1 squared? 1 times 1. 1. Now, remember, it's not going to really do much breaking out because it's just a 1. That doesn't really help me. But the next ones will definitely help out, like 4. Right? How did I get 4 as a perfect square? Well, that's 2 times 2. What about 3 times 3? 9. 4 times 4? 16. 5 times 5? 25. 6 times 6? 36. 7 squared? 49. 8 squared? 64. 9 squared? 81. 10 squared? 100. And then here we go. 11 squared is 121. 12, 144. 13 is 169. 14 is 196. 15 squared is 225. 16 squared is 256. 17 squared is 289. 18 squared is 324. 19 squared is 361, all the way up to 20 squared, 400. Now, I'm not asking you to memorize these numbers, but it would be good to keep this list pretty close by because it's a quick way to check perfect squares, as we're going to talk about in just a second. Also, don't forget, you can check perfect squares here, okay? If, let's say 80 pops up, and you're like, well, is 80 a perfect square? Well, let's look. Second, x squared, 80. Does it escape as a whole number? Nope. So it gets trapped inside. Now, we might be able to break it down, and we're going to talk about that in a minute. So here are your possibilities. Case 1, it's a perfect square itself. If it's a perfect square, like I told you, it gets to completely escape this prison, this radical prison, and it comes out as the square root of that number. For example, the square root of 4 would be 2. The square root of 9 would be 3. The square root of 16 would be 4, so on and so forth. But case number 2, what if it's not a perfect square? Then what we're going to do is we're going to break down that radical using the very largest perfect square that goes into it. So let me show you guys how this is going to look. If you take, oh, hey, there's one more thing, and it doesn't say it. It says if there's a coefficient outside the radical, you're going to multiply this by the number you take out. So let me explain that using some examples, okay? 49. Is that a perfect square? It's on my list, isn't it? See, it gets to completely break out of this radical prison as a whole number 7. It's out. Okay, there's no more radical because it gets to break out. I think you understand that, I hope. It breaks out of the radical. Look at 225. Is that a perfect square? Well, yeah, look, it's in my list. Go type it in. If you don't remember or have that list close by, the square root of 225, it comes out of there as a 15. So completely escapes this radical prison. Okay, look at the next one. 144, sure enough, perfect square, right? You can go look. The square root of 144, it's 12. It gets to completely escape as a 12. Now remember this little note right here. If there is a coefficient, a number, outside the radical, like that 2 is, you multiply it with whatever number got to come out. Well, what number got to come out? It wasn't 144. It was the square root of 144. It was 12. So this becomes basically 2 times 12. And now that they're both out of the radical, we're allowed to multiply them. See, I can't multiply the 2 into the radical, but once this comes out of it, I can. So 2 times 12 equals 24. I hope that makes sense. Again, if it doesn't now, it will. Now, sometimes you have a fraction. And in this case, even though it's a fraction underneath this radical, both 4 and 9 are both perfect squares. So they both break out. The square root of 4 becomes a 2, and the square root of 9 becomes a 3. So the square root of 4 over 9, it busts out of that radical prison as a 2/3. Same with number 5. Square root of 1 is 1. Square root of 81 is 9. So it breaks out as a 1/9. Now, last one, and then we start getting into some more problems where we have to think a little bit harder. 36 and 121. Look, they're both on your list above. 36 is a perfect square. But even if you went over here and typed it in, and I did alpha y equals number 1, I must have clicked something too fast. Alpha y equals number 1, and I did 36 over 121. Sure enough, it's going to do it. It's going to let it come out of there as 6 over 11. Okay, so these are the easy ones. These are case number 1. They're perfect squares, so they completely come out of your radical. But look at the next one, 112. Okay, go to your calculator. The square root of 112 is 10.58. That it doesn't escape. Now, don't go to your paper and write 10.58. That's unacceptable. Remember what I said, the only things that are allowed to escape out of these radical prisons are perfect squares. And you see 10 can't escape because the 10 squared, 100, won't go into 112. So what we have to do is we have to think of the biggest perfect square, the biggest perfect square that divides evenly into 112. So here's my process, y'all. The smallest number I'm allowed to divide something by is 2. So I divide whatever that value is by 2, and I don't try any perfect squares above that number, okay? It'd be a waste of my time. So I go up to my list, and I say, okay, 56, where do you fall? You fall right here. I ain't even going to try any perfect squares that are above it. Because again, the smallest thing I can divide a number by is 2. So there's no way 64 or 81 or 100 or none of those numbers are going into it. But these that are below 112 divided by 2, 56, these could potentially. So instead of just saying, hey, I wonder if 4 goes into it, or I wonder if 9 goes into it, I just quickly take my calculator and I start dividing by each of these perfect squares until I find the one that goes into it. It'll save me some time in the long run. So here I go. I go 112 divided by 49. Does that go into it evenly? No. 112 divided by the next one, 36. Nope, closer, but no. 112 divided by, I'm positive 25 doesn't, but I'll check it. Nope. 112 divided by 16. Bingo, there it is. 16 goes in there 7 times. So let me show you what this means. We're going to go down here and we're going to change this square root of 112 to the square root of 16 times the square root of 7. It's like we're breaking the number 112 down. Why did I use 16 times 7? Because remember, 16 is the biggest perfect square that goes into 112. And perfect squares are the only things that are allowed to escape radicals. So 16 gets to escape this radical as a whole number 4. It's out. It's out. It stays outside my radical. Now look, the 7, it can't go anywhere. It's stuck. There's no perfect square that goes into it. So simplifying the radical square root of 112 equals 4 times the square root of 7. Now, just so you guys can understand, if you're taking a multiple choice test, you can check this. Let me show you. When we did the square root of 112 a minute ago, it was 10.58300524. But look at this. If I did 4 times the square root of 7, guess what? Identical. These are the same values. It's just been simplified by pulling out the greatest perfect square that goes into it. I hope that makes sense. It's not that hard, but people struggle with this. In my years teaching it, people struggle with this. And it's not as hard as we sometimes make it. So think, the only thing that can come out of a radical is a perfect square. Okay, look at number 8. Let's check it. The square root of 2, 4, 5. Is it perfect? Nope. It wasn't in my list, so you probably knew that anyways, but it's definitely not. So here's what I do. I divide it by 2. Now when I divide it by 2, I know it's a decimal, but it doesn't matter. What I'm doing is I'm trying to find a starting point, okay? I'm not going to try any perfect squares that are above this number, because 2 is the smallest thing you can divide something by, and it gives me 122.5. So there's no way these numbers could possibly go into it. So I'm just going to take my list, and I'm going to take these numbers, and I'm just going to work my way down so I can find the biggest perfect square that goes into it. So here I go. 245 divided by 121. And I know that doesn't work, but I'm just going to show you how quickly you can do it. 245 divided by 100. I know it doesn't work, but there it is. 245 divided by 81. That's not it. 245 divided by 64. Whoops, not ln. 64. That's not it. 245 divided by 49. There it is. 49 is the biggest perfect square that goes into 245, and it goes in there 5 times. So how do I break this down? I go change it. Okay, instead of it being the square root of 245, I make it the square root of 49 times the square root of 5. Okay? Remember, perfect squares, that's the only thing that can break out of this radical prison. And it breaks out as a whole number 7. 5 cannot break out, so it stays inside. So 7 times the square root of 5. Now double check it. Remember what square root of 245 was? It was 15.65-ish. Let's see if we did it right. 7 times the square root of 5. Perfect. We simplified that radical perfectly. Okay? All right, let's go to this next one. All right, 5 times the square root of 72. Now, ignore the 5. Let's check the square root of 72. Nope, that don't work. All right, that don't work. So we're going to try to break this down. Remember, I always like to divide it by 2. That way I can find a starting point. So 36. I'm not going to try any perfect square. Let me erase the one that we did earlier. We're not going to try any perfect square above 36. Well, what do you notice, guys? It is a perfect square, 36. So that means I am breaking this down, leaving the 5 alone. I am changing square root of 72 to 36 times 2. Now, remember, right now they're both stuck under the radical because I'm just breaking 72 down with the biggest perfect square that goes into it, 36. Now we let 36 escape the prison because it's a perfect square. It escapes as a whole number 6. And then, of course, 2 cannot. Now, don't forget, there was already a 5 out there, and the notes that we read earlier said multiply those. So 5 times 6 is 30. And then that 2 in that radical just come on down. So it's 30 times the square root of 2. Let's go check it. Remember, square root of 72 was 8.48 blah, blah. Let's do 30 times the square root of 2. And, oh wait, I'm sorry. I was about to say, what in the world just happened? I forgot earlier, it was 5 times the square root of 72. My fault, y'all. So sure enough, now they're the same. Well, I looked at that for a second. I was like, wait, what did I do wrong? That's what I did wrong. I forgot to include that 5. So there was the value, okay? So there's number 9. Let's look at number 10. And I'm hoping that you guys are starting to see this a little easier. Look, 45. Let's see if it's a perfect square. No, it's not. So I'm going to quickly take 45 and divide it by 2. I am not going to try a perfect square above 22.5. So let me go back to my list. I am not going to try a perfect square above 22.5. Well, 22.5 falls somewhere in here. So I'm not going to try anything above that point. So I'm going to start at 16 and work my way down. So is 45 divisible by 16? Nope. The next one is 45 divisible by 9. There it is. 9 is the biggest perfect square that goes into 45, and it goes in there 5 times. So let's go back up here. Here's what we got. We've got 9 that was already out there, but we're breaking down 45 using 9 and 5. That's what I just showed you, right? 9's the biggest perfect square that goes in there 5 times. Now, remember, because 9 right here is a perfect square, it gets to escape the radical as a whole number 3, right? The square root of 9 is 3. 5 gets trapped inside. So on the outside, 9 times 3, 27. And then that 5 gets trapped underneath the radical. And there you have it. Okay, number 11, 250. Let's try 250. The square root of 250 is not a perfect square. So I'm going to divide it by 2. 250 divided by 2. I'm not going to try a perfect square above 125. So let's go back up to my list. Let me erase the one we had earlier. I'm not going to try any perfect square above 225. Well, what do you notice, guys? 225? I'm not going to try one above 125. I got ahead of myself here. 125 is about right in here. So I'm not trying any perfect square above this point. None of these could possibly. So let's start at 121 and work our way down. So 250 divided by 121. Nope. 250 divided by 100. And this is not hard, okay? So don't complain. 250 divided by 81. Nope. 250 divided by 64. Nope. Close. 250 divided by 49. Nope. 250 divided by, what's the next one? 36. Nope. 250, here it is, y'all. We found it. 25. 25 goes in there 10 times. Now, again, I know it looked like we kept on trying them and kept on trying them. We did, but we couldn't find one until 25. 25 is the biggest perfect square that goes into 250, and it goes in there 10 times. So, again, because 25 is the perfect square, it's the one that gets to escape as a whole number 5. And then, of course, 10 gets trapped inside. So 5 times the square root of 10. And just double check it. Watch. If you ever are like, that don't look right, check it. The absolute value, or the square root of 250 is 15.8. And 5 times the square root of 10 should be identical. It sure is. And think about it. No other perfect square comes out of 10. Right? 4 won't. 1 won't. So that sure enough is the furthest we can break it down. Okay, last one. 3 times the square root of 578. 578. That's a big one. So let's take it and let's try it. Always try it first, because you might just not know. No, it's not. So I'm going to divide it by 2. I'm trying to find a starting point. Don't try any perfect square above 289. So let's go to our paper, look back at it. Don't look at any perfect square above 289. Well, look at there. 289, it is a perfect square. So we found it. It's 289. Now, 289 goes into 578 twice. So that's how we're breaking it down. Okay, 289. Now, don't forget about that 3 that was already out there. 289 goes into 578 twice. Because 289 is the perfect square, it gets to come out. Now, what was the square root of 289? Let's check it. The square root of 289 is 17. 17 gets to escape that radical. So we've got two whole numbers out here now. So we're going to go see what 3 times 17 is, and that is 51. So my answer is 51 times the square root of 2. And again, go back and check it. 3 times the square root of 578, 3 times the square root of 578 is 72.12489, whatever, blah, blah, blah. Let's try 51 times the square root of 2. Bingo, we did it. We have simplified all of these radicals, okay? Now, on the back of this worksheet, of this note sheet, you have a homework assignment. And it's got a couple problems. It's not got many. I only want you to do numbers 1 through 10. Don't even worry about 11 and 12. We won't talk about those for a bit of time. So on the back of this worksheet, do numbers 1 through 10. All right? This recording is like 41 minutes. So sorry you didn't have more time. But it's a pretty easy assignment, 10 problems. Okay? We'll see you tomorrow.